Is this better? Let me know. Okay. Let me know if it's unbearable. Nice. Nice. Okay, guys. Let's start. Sorry for the delay. Nice. Thanks. New microphone. What can you do? So this is this is Hidden's the Xenium Hidden's home GPU setup, FYI, which is awesome. But it's super cool. It's got like, what is it? 1, 2, 3, 4, 5, 6, 7, 8, 8 strong RTX, whatever it is. This is great, but not if you're not single, because what you can do then, if you are not single, you can also rent GPUs online. So we get a lot of questions on this, and I thought I'd go through it step by step, the super dumbed down version of how to do it, and then we take it from there. But you need to also realize that, so I will go through this tutorial. I thought I'd begin with that, how to mine Zen blocks with rented GPU. And then I go through shit ton of theory today. So it's going to be deep, just the way you like it. So there's many ways how to mine Zen blocks. There's many roads to going there. You're using the same miner, but in various different methods and processes. But we are finding the best practices how to do it. This is a process I like, but there's already things going on in the background. Smith is working on some really cool updates as well. But how to mine with GPU. So the first thing you do is create a GitHub account. And then I would fork Joseph's repo. So Joseph looks like this. He's a super Xenium, and he has a repo where you should go into this XGPU, and then up here, when you're logged into your account, you can just fork his repo. So that's the first step. The second step. The third step is you go into this address, vast.sh, and you change to your Ethereum address. So when you mine, you enter your address, and then it will mine to this address instead for the one that's there already, which is probably Joseph's. Or you can mine for him too. He would appreciate that. So what you do then, you go into the README file in your GitHub, and you choose, you go in here in the for single GPU, vast.h, and you can see this address needs to be updated. So you edit it and enter your name, the name you have on your repo instead. What you should do then is test the URL. So you just take this URL and see that something comes up here, just to verify that there's something there. You then create a vast.ai account, which is a GPU market. So people at home have GPUs. And this is sort of a platform where these peers can meet and rent. So it's an awesome way how you can just, with a click of a button, rent a GPU, and you don't have to be a super hash head like Hidden. So it's pretty cool that you can do that, first of all. What you do then when you're logged into your account is that you choose this image, CUDA level Ubuntu. There's people who have made different kinds of this, but this is a template you need. So when you rent a server, you have the right foundations in order to be able to mine Zen blocks. Then you need to add some funds to your account, and you have to set an SSH key. So this allows you to communicate with this with the server of the GPU remotely. So you have instructions is just follow. When you try to rent the GPU, this will come up. So for Mac or Linux, you just follow these steps, works super fine. If you have Windows, I would suggest go to 3CD West's account, GitHub. He also has with instructions how to do it. He also has a YouTube link, which is awesome. Then you rent the GPU. I will show you how to do this. So in the search, you choose include unverified machines. But then you choose this based on some parameters. So then the question is like, which machine is good for mining GPU, and with the GPU, and it also depends on price, what you have to pay for it, because you pay by the hour. So you load your credit and you pay for the usage of this machine. So you can start it and terminate it, give it away at any time. But I did some comparisons of different machines, so you can see here during the last couple of weeks here. So just to see the performance of different with the same hashing algorithm that we use. So you have, and this is very, very nice to see over time, because this is sort of the proof of work that you have to do in a way, that you have to find, you have to do mining, but you have to do it in a cost-efficient way. So what we can see here, you have a $1 per hour price, and you have the output of this machine, which is hashes per second. But what's even more important to look at is basically hashes per second per dollar spent. So this is a much more interesting metric to go by if you want to be efficient than just going by hashes per second. So I would suggest you do that. What's also interesting to look at, if we see A40 is a very good GPU. It's one of the best. And it produces a lot too. But if you compare it to this RTX 360, it has an even better value than the A40. So you can find these good and sweet deals. So I suggest you just try it out. But anyway, so there's a whole science, not a whole science, but a bit of a science. But I just gave you like the book of how to think about it. So then you connect to this GPU inside the terminal, and then what you do is you copy this vast link from your GitHub that you forked from Joseph. Ribbit! And then so you just take this link that references the whole script, and then you run it in the terminal. So when you run it, you're actually going through all of these steps that we did last time, if you remember. And then so then you run that script basically, and it starts the miner. But then to see the miner, you have to put in these commands. So once you're connected, you go into the directory where the miner is, because in the code you tell it to log all the actions, so you can see these actions that are happening if you put in this in the command line with the miner and with the Zen GPU miner. So let me just show you. I lost my breath. So blah 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 blah. Here we go. Can you see? Yeah, so here we have Joseph's miner. Here is his GPU directory. So you just press fork here. Here you have the actual code. So here, now I'm logged in to, oh shit, I only have $4. So let's go to search, and we hit unverified machines, and then we can take some Forex. So I just rent, but now I'm doing it live. So sometimes, and this can be good to know too. So now when you rented them, you go in here to instances, and this is where you can see them. So it takes a while for these to start. Sometimes it's a few seconds, and sometimes it's much longer. Yeah, here we go. So that's nice. So then we can skip it, but we save them for now because we might. Sometimes it doesn't work to connect with the miner also. So let me go in now to the terminal. Is it this one? Yes. Bam. So now I just pasted that link with the SSH connect. So then I just says yes to whatever they say, and then hit in the password. So now we're in, and what we do now, we go back to the directory that you forked from Joseph, and okay, I'm just going to take his in the README file, in the directory, and then I take from his repo, works as fine. Bam. So now you can see like the whole process that we did last time automatically. So it updates the package and the necessary package list, installs HTOP, Python, it cloned Woody's GPU repository, builds the environment, updates the config.conf file. So it updates with your mining address, and it installs all the requirements. It starts the miner and the GPU miner. So it does all of these things now. And all you did basically was find the GPU, rent it, and deploy this code. And then it's just like in the old days, in the 90s. It goes to 99%, and then it stops forever. But it's nearly there. There, it's done. So now it's running the miner already. It's hashing for you. But we want to go into the directory, and we want to use this command that I told you about, the miner. Bam. Here we can see that it has a hash rate of where's my here? A hash rate of 5,000. Oh yeah, okay. Yeah, sorry. And it's mining. So let's go to the Zen GPU miner and see what that tells us also. There we go. So now we can see that the difficulty is 79,400. We can see the hash rate on this one. So now I entered one of the four. It starts 0, starts at 1. Or 1 starts at 0. Anyway, that's how easy it is to mine with the GPU. Now let's go back to so this process I basically recommend for everyone to try out this way first. But I think this is the best process now to learn all these different steps and to understand what you are like, what you're doing. So I would recommend that. But constantly, everything just people are making it better and better and better and better, and that's what's really cool. So right now, Smith has made this, and I think Woody was in on it too. They made their own template or created one within Vast, which has the GPU miner like attached to it. So I think maybe in a few days or a week, people will do this instead, because then you don't have to do the whole GitHub route. You can just go to Vast and yeah, plug and play from there, basically. So basically all you're doing, I tried this yesterday, it worked for me. You rent a server, basically, or a GPU, where you have this image instead. And once you connect to it, to your server, you just enter these commands. So you change directory, but then you have to do the old way of nano config to conf and update the miner. To update your address. and then you use this command to start the miner. So that's pretty cool. Jack also has some code. There's many roads. I like what CryptoBra is saying. I like my 15-step guide to mint Zenblocks because you can get under the hood with the miner when installing the commands into your cloud or locally hosted GPU. If you go straight for the one-liner and you have no clue what you're doing, you deserve the headache, homie. So he also has follow. If you're not following CryptoBra, I don't know what you're doing. So follow CryptoBra. He is awesome, and he made this guide as well, where so you can do it more the old school way. So and join the Zenblocks group because that's a lot of hash heads there. And the definition to become a hash head is that you at least mined one block and got one Sunni. That's it. And then you have Tricity Vess also made this awesome explorer that you can use in terminal. You should try that as well. So that's pretty cool. This is a must. I go here every day, zen.pub. So you see all the statistics from the miner. So this is, I think I took this today or something. So it's around 4,000 blocks that's been mined. We're going to talk about tokenomics in a while. The current difficulty, we're going to talk about that a lot today as well, etc. So you have all the stats, and you can also check with your individual address. So those are like the basic things if you want to get on and start mining Zenblocks. So let's go into the matrix now. So before we continue with CryptoBra saying this is community bit. It really is. It's like insane how much the team and community have been involved in creating something together with this. It's super cool. A lot has been done in a short amount of time. But the question is that many have, of course, like how is this all fitting together somehow? And it's a very good question. So we set out to make the best infrastructure possible, and that's what we are trying to do. And this is the matrix as it looks now, which is ever changing for various reasons. But that's how it is. But this is our matrix that we can build. This is one vision of it, where we have no censorship, where we are free to do whatever we want. So this is just a vision. But how it could look like is that X1 runs fast EVM. You have sub-second block times, inexpensive transactions. You have fast EVM execution, scalable, using DAG. So X1, you have a very good overall strategy as well with tokenomics, which will make the chains very decentralized and get proof of protocol-on liquidity. You have power features giving Zen utility for the next 10, 20 years with burn records. It's optimized for adoption with users on all chains. On the tech side, we're working on updated version of Fastnet there with our own customizations, attract developers and optimize the code, etc. With Fastnet, we've shown how we can make it scalable, being able to handle high traffic, fast execution of transactions, etc. So we're happy with that. There's no need to rewrite good EVM code. It makes sense to reuse Solidity. And this will give us a platform for EVM compatible DeFi ecosystem. So most important right now is to build the tech so good, and so expectations are also in line with what you will burn for, because we also need to demonstrate bridging to and from the ecosystem and stuff like that. So then first we can pin down more exact tokenomics, start auctions and such like that. So from a tech perspective, we're doing good. We're doing really good. We're going from clarity to clarity, I would say. But with X1, we also need to think about security. And a problem with proof of stake networks, especially when the value is low, so it can't be susceptible for attacks by an adversary with a large amount of capital. So with proof of stake and tokens are not worth any work. So technically you can get or potentially, hypothetically, you can get unlimited amount of tokens and influence the validator's function, even with a fair distribution. So it could be put up for sale, dumping on the market for pennies, and someone could come in and buy up all of them and put in a position of control. So to mitigate that, we want to leverage proof of work. And during the last weeks, Zenium has evolved, so which is a proof of work, proof of stake hybrid. With strong consensus, we have 15,000 miners and it's growing. Blocks produced are blocks that people own, so it's very cool for self-custody sense as well. So, but the gist of delegated consensus is you separate the transaction execution layer from block creation. So Jack calls this delegated consensus or delegated proof of consensus. So we have a proof of stake layer to handle fast transactions using 21 rotating nodes, whose main task is to assemble lightweight blocks from transactions in a network, propose these blocks for further validation and finality. So we call these block proposers. To the proof of work layer, which consists of an unlimited amount of proof of work miners who perform validity and consistency checks of the on the proposed blocks and vote for their accuracy. So all or many of them do this, and votes gets propagated in this peer-to-peer network to find consensus and finally settle with an accepted block to the chain, which then also becomes immutable. So security, decentralization, and scalability. But we're thinking it could be cool to integrate these two solutions together, that X1 is a client that handle all smart contracts. X1 will be the EVM layer on top of ZenBlock's hybrid system, where contract execution is handled with X1 and settled with ZenBlock's layer. Zenium secured. So X1 EVM layer, the contract handling layer, plugged in on top of Zenium network, secured by ZenBlocks. And then we have strong networks where we can reach EVM and Bitcoin ecosystem. So with VNPX, we know how to transfer value between Ethereum and Bitcoin. It's just needs to be secured and plugged in into this multi-tiered hybrid in the most efficient way. But in all and everything, I feel, or I think, if you're talking about my feelings, for once, that I'm just kidding, but that we start to finally diverge into a collective, more complete system in a way, even though things are changing all the time. And today I want to focus on Zenium completely, because in order for us to understand if this is a good solution, then we need to understand Zenium like to the bone. And Zenium is pretty cool. Warning. So I'm pretty amazed with things I see and Jack do, like basically every day. So but here's the thing as well, because the way I see it, the question is which ingredients will make the overall best soup, because it's all about the ingredients and the assembly thereof. So let me give an example of this. If you take the world's biggest company, Apple. So what is it worth? $2 trillion or something like that, way more than the whole crypto market. What was it that made them like really successful? They had many stuff, but one thing that really made them a lot was the iPhone. So that's an interesting innovation, because you remember back in the days, you had BlackBerry, you had all of this. You had Nokia was super big on my time. Do you say that? On my time. So but what was it that made the Apple grow so big? And it was because they weren't the ones who invented the smartphone. They didn't invent the internet processor. They didn't invent the touchscreen. So what they did, it was the assembly thereof and the packaging and the message that separated them with the iPhone. So another example is Bitcoin, because the enabling tech is not really novel in itself in many aspects, because Satoshi did not invent blockchain. He did not invent proof of work or Merkle trees or peer-to-peer. He just brought them together. Proof of work, invented by Adam Beck, I think, had been used in email to prevent spam and stuff like that. Blockchains existed before. Merkle trees was already invented. Peer-to-peer solutions existed. I used to download from Kazaa and Pirate Bay and all of this stuff. I'm sure many of you did as well. So Satoshi did invent, however, Nakamoto consensus, however, which I will talk about later, which is very cool. But it's what we do is just research with the community and build the best ideas through empirical and open testing to find the very best solution to common problems. So that's just like some sort of vision. But let's dive straight into ZenBlocks, because this whole stream is basically based on my previous stream about ZenBlocks, where I talked about hash rate, what ZenBlocks is, superblocks, Sunnis, leaderboard, fixed global hash rate, the difficulty adjustment mechanism, mempool, the state, blockchain DB, sync node, sealed blocks, Merkle trees, block voting. So those are important aspects to still understand. So it's still valid to a large extent, all of that. But the biggest difference is that GPU mining took over more or less completely. Would crack the code. So let's just begin with an overview of some of the key aspects of the key features of Zenium. So first you have Argon 2, which is the cryptographic hashing algorithm used. So the heart of the system engine. So you have memory hard computing, which is what makes ASIC mining ineffective. The difficulty adjusts based on the network competition, tying increased mining difficulty to memory allocation. And we have this adaptive difficulty. So because of that, we can decouple it from energy use, and especially large energy use. So I'll talk a bit about that. But we also have this hybrid consensus mechanism. So we take the best from proof of work and proof of stake by separating the executive layer for confirmation and settlement layer for finality. So we can get both speed and security. Tokenomics is pretty simple, but it's also important to realize that the reason it was enabled with a token in the first place and not use the blocks as we thought in the beginning is to enable proof of stake. So you have a supply estimation of around 620 million XNM. So with a yearly halving. So that's what you get. So today, around 0.5% have been mined of that. So we're super early in this distribution that started from zero. So you have compatibility. It's also compatible with MetaMask. So if you mine it right now, you have them in your MetaMask. You just have to add the ZenBlocks RPC. So we can elevate that network for adoption as well. There's many things of these aspects that are crucial for the system. So system architecture, let's talk a bit about that as well, just some key components that's good to know. So you have block proposers, proof of work miners, You have 24 validator nodes, so they gather transaction from the network, they do preliminary validations, they propose a block, so-called lightweight blocks, and then proof of work miners. So as distributed network perform deeper transaction validations, vote on accuracy of proposed blocks, confirm these to the chain for finality. So life cycle, you initiate, transactions come from Ethereum compatible wallets, and then this proof of stake nodes validate them. There's a queue system that for efficiency. I will talk about all of this stuff. Voting as well. So proof of work money is vote for the block's accuracy. I showed you this last time with the block voting. So a block requires a majority of votes. Finality, blocks that have a sufficient amount are distributed to peer-to-peer network, and then it becomes immutable and final. And when it comes to network security and incentives, this is actually like super interesting, because when you mix proof of stake and proof of work, you have chains who are one and the other. But if you start like mixing them together, you start to realize that there are many things that you can really leverage, both strengths. It's like 1 + 1 is 3 almost. So that's very cool. We'll talk about that too. We're going to talk about that. So the benefits can be summarized as speed, because you can achieve near instant transaction confirmation due to this division of labor between proof of stake and proof of work nodes. Scalability, you can allow for very high throughput, because validation, confirmation, and block proposal happens in parallel. Also transaction validation and block proposal. Energy efficient by utilizing proof of work miners, validation and voting. Yes, this is true, but also because of that there is more or less a fixed hash rate. So you're not using more energy the more miners come. We'll talk about that. And then security. So we talked about that. So here is basically, so I will go in detail, but here is the way to think about. I should be better with. Let's do this so you can zoom in a bit more. Looks a bit small. But yeah. So here's how you can imagine it. There's these two layers with the Xenium. So you have the executive layer to propose and achieve fast transactions, and you have the settlement layer for the purpose of security and finality, settlement and storage. So the execution layer, imagine it as fast and small. So its main purpose is to handle the transactions and give very fast confirmations. So and its task is also to produce these lightweight blocks. So they're specialized serverless nodes. There's a small number of them to propose blocks and handle transactions. And if the production is like at most 21 nodes, then we can achieve the speed of like Antelope and Solana. So it's the lowest number of supermajority would be 11 that need to sync very quick, which is very low, but they're only block proposers and will be slashed if wrong, and the miners are doing the validation. So yeah, that's sort of the overview of that layer. And then you have the settlement and storage layer, which is more, imagine it as more huge and slow, where the proof of work, it's still fast, but the proof of work layer to handle validation and finality, right? So they assemble bigger blocks from the lightweight blocks that are coming in. And this is comprised of this huge network of unlimited nodes to store and sync the state in the peer-to-peer network. So and we can achieve immutable storage very efficiently with B-tree, which I will talk about today. So the way transactions are being secured is by having these miners produce the blocks. So the miners who are the system validators will also have to stake Xenium and will get slashed for malicious behavior. So that's why it's sort of like, this is how I see it. Like, you have this proof of stake layer and then a proof of work with proof of stake incentives as well. So yeah, but the gist of it is that it is a separation of these two layers, block proposing from block production. So what we have is a system with dual consensus, dual confirmation, sort of like an L1, L2 relationship. And there are, of course, references to how others have solved this duality before. So Ethereum has a series of consecutive transactions, right? And that makes them slow. So every transaction waits for another transaction. And the solution for that is sharding, or L2, like Arbitrum and Optimism. But with that, you then have these two different foundations for governance and for the chain to last through everything that needs to be done in the time being, and the human interaction in those decisions, which could be a thing or could not be a thing, but it's a thing. So there's also parallel with this to Bitcoin and the Lightning Network. So Lightning is fast, Bitcoin is slow and secure. Cardano uses high. Xenium, with Zenium, this separation occurs in the same network, very optimized to work in conjunction. So that's a way how I look at it after interpreting Jack's visions on it, which is pretty cool, I really think. Now, so let's open up the hood on this and open it up in like way more detail, how it actually works. So are you still with me? Sometimes I don't know if these things lag. I need to use this system that everyone else uses. Yeah, okay, nice. So this is a much more detailed view of this process, how it could look like. So you have proof of stakers that propose blocks and handle all the transaction. The main objective is to confirm transaction and to do so in the fastest way possible. You have proof of work miners to act as validators of the data, whose objective it is to settle the transaction and reach finality. So you get a bunch of transactions from the network. The 21 proof of stake nodes pick up these and validate them. And just parentheses, like, they're also proposing difficulty adjustments. So they have other roles, etc. So I will talk about this later, but just for you to remember that they're also doing other stuff. So this is for the block proposal production. Confirmations happen way faster, but they don't do all of these steps. But they put the valid transaction and place them in a queue. Transaction ordering is happening. They assemble the transactions into lightweight blocks, and they make then a block proposal with header, metadata, ordered list of transaction, and signature and stuff like that. So this is what they do when it comes to the block proposal part, and that is the separation. That proposal then goes to the proof of work who received that proposed blocks, and he will not be so fast. He will say, "Hey, wait! This is like this is like an Italian, okay? This is like an Italian from New York with a baseball bat. Hey, you talking to me? You're talking to me, block producer? Give me your block. I will." Yeah, he has an Indian mother. You're talking to me. I will investigate this block. I will really look at it. So he performs this consistency and validity checks. He includes the balance verification, the double spend blocks, and yes. And then they use proof of work voting. So they're using the hash of the block to propose Merkle and vote for accuracy. So this is what we talked about last time with block voting. And then they broadcast this vote to the whole peer-to-peer network. And once you have X number of votes, you have consensus, and the block accepted becomes immutable. So, and then if that happens, then rewards can be distributed based on what work has been done to the block proposer, or the Italian here with the baseball bat, who will slash him if he does something wrong. So they are proof of stakers. So they have a stake in providing the right data. So this is also why it's interesting to see like how far can you push that, which we will do later. So here in the model below, you can imagine it as like lightweight blocks becomes settlement blocks and immutable after verification from all of the proof of work miners. So decentralized chains of data, they have these two major components, confirmations and settlement. So Solana chose to optimize confirmations, but they are using more flat design where any node can do anything. They remove the concept of nonce. They're using proof of history for that instead. So they do have the election process, but it's based on proof of stake purely. So it's more centralized than proof of work voting, for example. So yeah, we will get into that. But this can take like sub 1 second easily, and I will show you why. Jack has shown me his tests for the last 2 days. It's pretty cool. And so that's the same as Solana has like 400 milliseconds for this confirmation. Settlement could take like 30, 60 seconds, just as Solana. How we're looking at it now. So 200 milliseconds is what Jack told me today, like would be really cool. Solana's 400 milliseconds. So yeah, and they have 30 seconds blocks. So if we could aim to be the same. Confirmation, so the confirmation time being 200 milliseconds, that's how fast our leader, which I will talk about next, reaches at least 3 other geodiverse nodes that confirm that the transaction is valid. So block proposing is asynchronous. So they serve storage and the immutable layer, but if you have like 1,000 transaction per second or 50,000 transaction per second, the block times don't affect the confirmations. So in Ethereum they do, because confirmation for end users should be near instant for us. So confirmations and block production happens in parallel with Solana. With Ethereum and Bitcoin, it doesn't. So that's why they're slower. So they need consensus before confirmation even. So that's what the Jack calls delegated proof of consensus. So Solana sort of does it too. Solana uses stakers to provide the votes that we do with the miners here, and that's a major difference for these two systems. So stakers have social consensus of the possibility of getting slashes, but Solana stakers, they can cheat, they can Sybil vote. Our proof of work miners, they can't Sybil vote since they have to produce a block first. And that's huge. That's alpha, I think. That's super interesting if that holds up. Because that's sort of that's cool. So and Jack set up a Solana node so we can test this stuff. We'll talk a lot about Solana, but it's because they're fast, so you can't talk speed with Vitalik chain. But we talk about Ethereum a lot too. Let's see. Yeah, so the proof of miners can't Sybil votes, and they have to produce a block first. So fast confirmations plus security is what's at stake. So yeah, read about the homework. What is the difference between finality and settlement? And then we move on. So the peer-to-peer network. Yeah, let's talk about that, because all of this that we show now, the processes, seems is going on in this completely decentralized peer-to-peer network. So just like in Bitcoin and Ethereum and any chain, you have a variety of types of nodes. So you can have light nodes who sync the chain, but don't have a full copy. You have full nodes who can extract the data if they want, but they have the Merkle's accessible, or just an example. Or you have full archive nodes that have like everything unpacked and can reach everything immediate. So different nodes for different purposes. There's light nodes and prune nodes. So light nodes are similar to prune nodes, pruned full nodes, in that they have some, they can save up storage by downloading just select information. But light nodes are much more limited. So in Bitcoin, the light nodes only contain block headers, which are codes in each block signifying that the block is valid. And a pruned node, it's a type of full node, but it allows to take advantage of a lot of security. So by reducing their blockchain storage requirements, they can run on basically any device. So exactly what kind of nodes we will have in this network, we don't know. It's just a demo that there are different kinds of nodes in the peer-to-peer network. So what we are doing right now, what Jack's very busy with, is playing with these peer-to-peer, these nodes for block proposers positioned in different geographical regions. So he set up 3, I think more now, block proposers for testing. And each one has a schedule for who is the leader, which I will talk about next. So they rotate each 1,000 blocks, and they run peer-to-peer. And he's been able to reach 110,000 transactions per second on these tests. So that's very cool. And here you can see the so here you see the Chicago, Virginia nodes where the ledgers are aligned. So you can see here the block ID number on this location matches this location, and here you can see the hashes. And that's pretty important to understand when it comes to like peer-to-peer nodes, that they don't have to sync like every transaction. If both have run, if both have their local state of the chain, you can be a light node and still check. I think it depends, but you can still sync that the Merkles of that, because we talked about how Merkle trees work last time. Like if you change just even one number, it's going to change the whole sealed blocks Merkle. Yeah, so that's pretty cool. And these 3 nodes sync in Chicago, Sydney, and New York. And this is very cool because so he showed here that this can be achieved with all 3 nodes. And the New York to Sydney, let's see which one is that. It's this one. So that we can see it's. Can you see my mouse? Huh. Okay, you can't see my mouse. That's annoying. Let's do this. Haha. So yeah, so you can see there that message took 100 milliseconds. So how much is that? So I was like, okay, how fast is that really? So let's check. So between Sydney and New York, it's this distance, okay, in miles. So because Americans, we have to count in miles first, and then meters. So we take that to meter, and then 100 milliseconds, that is 0.1 seconds, right? So if we take the distance divided by time, then we get 159 million milliseconds, which is 50% of speed of light. So that's how fast it, like, just to get an idea of how it's like, it's like faster than that even, super fast. Anyway, just to get an idea, like what levels are we talking about here? So yeah, so what we're saying is basically that the transaction confirmation will be as fast as the network can possibly be. We are as close to raw performance as possible with this test. So we could potentially have faster confirmations than Solana. It would be really cool to see if we could do that, because to do this, we're using real-time communication libraries that are used for voice and gaming and stuff like that. So Jack's benchmarking Quirk and WebSocket, he should really talk about this, because I don't really understand how they work. But Solana uses Quick. They have something called UDP before, but that was one of the reasons for their system to crash a lot. And they have 400 milliseconds, and our test shows 100 for this. So if you add a little bit more, it could be like 200. So that's that would be very cool. So the question is why they are not faster than this, which is interesting. But that could be many things. It could be to the proof of stake consensus, the proof of history having to run consistently or something like that. Maybe not. Maybe I'm completely wrong. It could be how they encrypt data, which makes everything slower. It could be over engineering. Jack talks about this stuff a lot. Like, he's very he says these things a lot. He thinks a lot of when he looks at everything, all the code. He just thinks that there could be much better solutions. A lot of them are over engineered. So there's a reason why, when Elon Musk deletes 80% of the requirements or whatever he does, he just streamlines everything. So it's like it's the same concept. And so the reasons for why something might be over engineered is because many engineers just add a lot of garbage in the code for job security and for vanity reasons, stuff like that. So and I will come into soon that like other differences. So there are many things that you can improve a lot, we think. So we don't see how this could be any faster, because the speed of light already almost. So that's probably not the limiting factor, because Jack could send this at 110,000 transactions per second. And so we could decode in the CPU that it should be at least 75,000 at most, or something like that. But then the CPU will be the bottleneck before the lightning speed. But CPUs get faster and faster too. So let's see. These looks like fantasy numbers, but in the same time, they're empirically tested fantasy numbers, which is pretty cool. We're just shocked by these. But this is confirmation. It's not settlement. They are separate. You need to separate the two always. I forget my mouse over here. The red one. Okay. Right. So let's go. There's probably a setting where I could use Miro and have a big mouse, but I'm not going to find it now. So the question is, how do these nodes sync? Just to get an idea of that. So basically, a node, this you can do already now. So you can just download and run sync node. So you're pulling data from the chain, and that it stores that data in a local blockchain, in a local state. And then you have this network of different nodes who have their different versions of the state. Just as simple as that. And if we're going to complicate it, we can see, like, okay, what is it actually that they're doing? Forget this is annoying. So here's the process. Like, if you're becoming a node, this is like fundamentally what's happening. So first you do an initial sync. So you're downloading the initial blocks. So when you run sync node, this is what you will see. that you've downloaded all these blocks, and all blocks are valid. What you then do is you're processing the blocks. So you're executing all transactions in a blocks in order. You're updating the state and modifying the state of the account and building a Patricia Radix tree. So this is what you do in Ethereum, what we will do in B-tree instead. But it's the same concept. So the nodes take all the transactions from all the blocks and then modifies the state. So you're transferring, if you're transferring Xenium between two accounts, it will update the debit and credit for account plus minus. If you're creating new accounts, if you're invoking or calling smart contracts, etc. So it does all of that. In Cardano and Bitcoin, they don't have this accounting model, so they don't do this. But Ethereum does, and Zenium does, and then it updates this local chain with the changes, and then you update the state trie. So you update the whole picture, the whole books, the bookkeeping. This is just electronic bookkeeping. Yeah, and then digitalbookkeeping.com. we're economists. So we store intermediate states, and then you have a completion of the sync. So all the blocks are processed, the nodes in the sync with the network. It listens to new blocks and processes them in real time. It updates its state tree accordingly. And now you have a current state of the SAM block running on your device, wherever it is. So let's see what the requirements are in different kinds of nodes, what different kinds of nodes and what the requirement to be one will be. But now it's pretty cool that we can see already now, like the complete picture in a way that, okay, yeah, this nodes can talk to each other, they sync, they share data, it works, it's fast. It's Xenium. Anyway, yeah. So yeah, what we should talk about also, yeah, let's talk about that because it's important. Is Nakamoto consensus really? Yeah, let's do that. We have time. We have hours. It's gonna be hours. So just FYI, when we're talking about peer-to-peer communication, so we need to talk about Satoshi Nakamoto and Bitcoin, like what it was that made them legends, because it's really regarding trustless scalability. So the challenge is how you're going to reach consensus at large scale. So the best way to describe this comes from the story of this Byzantine time generals that were going to attack a village at a certain time from the no let's do a better story. So you have me, you have Jack, you have Crypto Bra and Crypto Kindness. We're going to attack Pulse Chain at 3 o'clock. And we're going to do it from north, south, east, and west. We're going to spread out. So we do that, and we spread out, and then, okay, 3 o'clock. But then I start thinking, damn, okay, was it 3 a.m. or p.m.? Because these are all Americans. And I start questioning, will they really be there, like at 3 o'clock? Because it will only work to take down Pulse Chain if we do it at the same time. So that's the assumption of the story. Because I might think, okay, maybe CryptoBra is not going to be there. Maybe he is DJing somewhere. Maybe Crypto Kindness is at a yacht or something. Jack is away creating a new token. So so you can't trust that they're gonna really be there. So what you want to do is send messages like to confirm. So you have messages in an adversarial environment, a hostile environment, and then the question is, what is the validity of this message coming from? Coming forward to me. So yeah, because it can be intercepted, it can be corrupted, it can be censored, whatever. So the question is, like, how do we solve this problem, where multiple messages are going to work in an adversarial environment? So the way this was done before Bitcoin was you had this BFT protocols. So it only worked with a known set of known actors. That was the problem with it. So you could only have a small set. And it required that all participants was known. So you have skin in the game with reputation. So PBFT didn't scale to more than hundreds of participants. So before Nakamoto consensus, no one of the protocols had this ability to do sanctions. And this was the thing with Nakamoto consensus. So Satoshi presented proof of work with Nakamoto consensus, and the BTC miners then permissionlessly, without registration, can turn on a miner and produce blocks, which is pretty awesome, right? It's not like you can go to the Fed and like, hey, I'm gonna print some money too. Like, you can't do that. But permissionlessly, you can do that with Bitcoin. You could. So, but you know, you still can. But it's enabled through punishment, because you have to spend a resource in order to being able to mine one. So it replaces this one person, one actor, one vote, which is how PBFT works, with one CPU computer, one vote, or one computational engine, one vote. So it's a very powerful idea how he could make that work, because you're never incentivized to try to mine a bad block, because you have this upfront cost. So double spending is an example. So you could try to send 1 Bitcoin to 2 recipients in a block, but it won't be accepted. And we can find consensus of that. So we can communicate to each other in an adversarial environment, which me and CryptoBra and CryptoKiness and Jack, we can't talk to each other in that environment. So that's pretty cool. It's also like, when you think about internet being the network of exchanging value, information, and what we are doing is building up the network to exchange value. If you separate like data, like informational data, so to speak, with value, or what we consider to be valuable, such as a Bitcoin, right? It's pretty cool that even with the internet, if I'm talking to you through the screen right now, you can't really be 100% sure it's me. I might be an AI or something. You know, but if I send you a Bitcoin to your wallet, you are like, yeah, that's my Bitcoin, because I can verify it on the network. So it's interesting to think about the difference between like data and value, and what the differences really are, because fundamentally it's 2 different, very abstract concepts, really, which are also very different. But anyway, yeah, it's just so amazing, like this whole thing with the distributed network, and how information and value can travel in a way that's not being able to be censored or anything. It's pretty cool. It's pretty basic with many peer-to-peer network, of course, but we need to carve out some time to realizing how they actually work in detail when doing something like this. So let's talk about these block proposers, these 21 up in the confirmation layer up here. Let's go into detail with them. So we have this 21 rotating block proposers, and so it's a list of 21 validators that's been voted in by POW guys, the proof of work miners. So these block proposers, there's some how they're chosen can be based on reputation, health, total timing mining in the network, total amount of XNM stake, network speed, CPU speed, the requirements. They need to stake XNM, must operate with a good hardware, must have mining history, or whatever it is. You define whatever you want them to be able to do within reason, because you want a large selection of them as well that fill all the criteria. And then you have an unlimited amount of proof of work miners who are the validators, right? So they continuously vote for the proof of stake block proposers. So we watch basically the best nodes then and running this block proposing. So these 21 nodes will then continuously receive votes from the proof of work miner nodes, which are unlimited in theory. But since they are distributed, you get the most fair voting with it, because proof of stake node is like a congressman or a senator, and a proof of work are the people. So if you do bad things, if they're slow, they get voted out, they get fired by this delegated consensus. So the miners always vote for the proof of stake nodes continuously. And that makes it very fair, since the proof of work miners are very decentralized. And this is where decentralization really kicks in, because a hugely decentralized network continuously vote for someone to take that executive action. And this is the delegated consensus. And Jack brought up this example of it being this republic. So congressmen are voted in every 2 years, but instead here they voted in every 5 to 10 minutes or whatever time slot that should be. So many forms of governance are just like this. It's a company as well. Like you have the board of directors whose main responsibility is to hire and fire the CEO. It's just like how much you want to cut down like the amount of decision, and what kind of decision is this small unit of action doer gonna do. In Sweden, you have to discuss about every little detail. You can never take any decisions. The French are worse. But we can take decisions, but we got to sit down and think of every option first. For instance, so that wouldn't work. The Swedish model wouldn't work. But that's the interesting dynamic, at least. So the delegation happens instantly, and it rotates. Because so number one, it's fair because the voters are distributed, and because you have voting with proof of work nodes, you're not removing any security in the decision making, because that ultimately makes sense for finality. So validators, the proof of stake validators, the proof of work miners, who are the validators, they also have to stake XNM, and they also get slashed if they misbehave. So that's why it's a mix of proof of work and proof of stake on those miners. So you're producing, you have to stake, and you can get slashed. So that's pretty cool. Yeah, and in Bitcoin, you create your value and then you go and sell it to the market. But here you can stake it instead. And if you're staking, you're securing the network, so then you're earning some reward for that too, probably. So yeah, but the obvious question here is, and this is like where we have to penetrate deep, is because, okay, so 21 nodes, it's very small, it's not decentralized. So why have it so low? And an idea is like how it works. If you wanted Solana or Antelope fast for confirmations, the lower the faster. But it doesn't have to be. It depends on leader selection, actually. So, but you can still double or triple it. But the question is it needed, and why? because you can make it more if you want. So just imagine if I'm an adversary with malicious intent. So first of all, I have to be chosen to become one of the 21, which is randomly selected from a wide selection. And with time, it's unlikely to get such a majority that would be worth to the attack. So this is so-called honest majority. So the assumption, which Cardano, Bitcoin, and Ethereum also has. So one being a block producer, I'm already there for a limited amount of time. And like 5 minutes or 10 minutes. So as soon as the network detects malicious transactions, I will also be slashed because I have to stake Xenium in the first place to be a valid block producer. So the slash amount or other penalty depends on the severity of the crime. But yeah. But the important part is the fact that the proof of work miners are choosing the proof of stake. They're voting for them, continuously incentivizing good votings based on good behavior. and the proof of work stakers who are chosen as a block proposer, they're also just block proposers. Okay, so it's the proof of work miners who do the real validation, the finality, and they comprise of an unlimited amount of validators. So the 21 proof of stake nodes are rotating all the time. They have stakes to ensure good behavior, the skin in the game, and they rotate with short intervals so they don't have to propagate a large amount of transactions as well. So then you have this concept of epoch. Okay. So epoch is so you can take the block proposing part and create epoch with it. So one epoch is a number of lightweight blocks. In the beginning of so this is if you want to make the process even more efficient. So you elect a leader out of this 21. You're now just going deeper and deeper into how much you can like scrutinize or like dissect in the efficiency matrix. So yeah, you elect a leader to be the block proposer for all blocks at the beginning of a block, and then at the end of the epoch, you choose the system chooses another one. So the leader is responsible for proposing all blocks in the epoch, selected at random based on node performance, transparent, verifiable way, whatever it is, whatever it needs to be. And then the benefit of this, it's just like, yeah, it's more efficient, more streamlined. That's the main thing. But if you do something like that, you also have to make sure that you have a contingency plan if the current block proposer is not doing his job. We have to have a backup. And the system must ensure that leaders are selected fairly, can't manipulate block content for their benefit. You need slashing to ensure that the entire process is transparent and verifiable by any network participant or external auditor and stuff like that. So that's also very important. Now, so for instance, what makes Solana very fast? They have this concept called leader rotation. So they call it single shard replicating information as fast as possible. But what makes Solana very fast is having one leader to receive all the transactions. And most of the other chains are leaderless. They can't commit to transaction without consensus. So what we are proposing is a leader to propose blocks to a very decentralized network of miners and validators. But this concept and that's the main difference between our solution and Solana, where that's the voting for the leader, like who is doing that, and that's where we differ a lot in the how, like who, in the how and the who is doing the voting, or whom's, one who, many whom's. So, but leader rotation itself is like it's way bigger of a problem that I thought initially, that I was aware of, because having multiple leaders per slot is a very big challenge. And it's something he said that's something I would like to work with for the next 5 years. And I'm like, damn, that's a long time to work on that problem. So it might be way more complex, what you think. But Jack has some ideas there, of course. And there's also like things you can do within that. So like there's something called leader follower model. You can have one leader for NFTs, one leader for regular transactions, and one for DeFi or whatever. And this is something that I know they are, I don't know if they implemented it or they're at least talking about it. But there's also other areas where I think we can be superior than this in a leader model, because if you think about decentralization, so it's like, so when we're talking about assigning leaders for a small instant, you're giving centralized power under strict controlled forms for a strict defined task with consequences for misbehavior. It's also important to counter in the fact of other forms of factors of decentralization. So look at the overall model. Hardware requirements, for instance, for Solana nodes is extremely notoriously very high, complex. And so there's something that maybe we can do better, and especially with tokenomics. So as someone wrote in the chat the other day, which I saw, which is pretty cool, is what makes a blockchain system centralized is not the number of nodes, rather it's centralized because those that control the majority of the supply also control some of the nodes' decision making, which is true. So decentralization is achieved when those that have and don't have most of the tokens share the power of running a blockchain. Not only share, but rotated responsibility according to a good system in place. Yeah, sort of. I mean, those who have are those who are also invested of being a miner and staker. But so they should do the voting. But I get the gist of it. So the token distribution done well, I think, becomes crucial for the security of the chain, because making sure it's decentralized, not pre-mined to a few actors who will have the control, makes it way better later on for ensuring that not only a few control the chain. So technically Solana is decentralized on a technological level, but they control a lot of the tokens and the nodes, and the cost, the tokens and the nodes, and the cost to run a validator is also very high, so very few can. So I like to show this a lot because I've done it many times. So if we look at Solana, for instance, the token distribution is controlled by insiders and VCs, and they also control a substantial part of the nodes. So out of 3,400 nodes, the dev team owns a substantial portion of these nodes. So what the actual level of decentralization is, you have a token distribution with initial investors 37%, pre-mined rewards 38%, and founder allocations with the 9-month lockup 21%. So is this like really crypto when you have that kind of system? Like, what's the point? Really, in a way, it feels like if my emotions matter also. So I think we can have like the way we are planning with X1 and Zenium, the way it's like started from zero and just the community, 15,000 miners, like, okay, boom, it's a pretty beautiful like start. So I think this is my point of all of this, taking you down this route. Like 0.1% of Zenium has been distributed now only. So it's also very high probability of decentralization for sure. So yeah. So I think there's going to be many instances when we look at stuff like leader. I think that's a good example. And who's going to secure the network you're interacting with. So whatever you're building on it, I think many of these other chains will suffer more and more and more based on the fact that we can do these things probably way more as fast, for instance, theoretically. That's at least what we're investigating. But if you can do it with a better tokenomics model at the base too, that's a very strong competitive advantage. So yeah, enough about that. But let's go to something else that's also fun. Can you still hear me? We got Rolando Aidan Dracic. Staradish Brate. Okay. Nice. All good, then I just continue. Fortsätter jag bara. So, yeah. Difficulty consensus. That's one of my favorite topics. I'm glad you brought it up. So, as I talked about in my last stream, we have this total fixed hash rate of about, I said 7 then. I didn't really DD the number, but it's more like 10 million. We should be able to get it like more exact, but it also comes with like more data in a way, because to really pin it down. So we should see what the total network is live for every miner. But I don't know if that's really 100% possible. But what you can do, you can quickly estimate it by this way. So if you have a total individual hash rate of X, and it's yielded Y amount of blocks in said amount of time, then the network is producing 1 block per second. So that's 7,200 in an hour. It's 84,600 in a day or something, but in an hour it's 7,200. So you then share that in relation. In relation gives a ratio that you can then multiply with your hash rate to get the network's total. You just do like I did here, and then you that's a very smart way how you can estimate it. Like if it's this hard for me to do it and I get that much, then it's probably somewhere around here. So there's a few assumptions in that, but it works pretty near every time I tried it. So, but the energy consumption is an important factor, because when it comes to proof of work mining, we can't generalize energy expenditure. Like all proof of work mining is the same thing. So Bitcoin is using and so these are the reasons why proof of work mining is different when it comes to what we're doing. So with Bitcoin is using SHA-256. It's a very old algorithm that's not optimized for low energy consumption at all. So the higher the difficulty on the Bitcoin blockchain, the more money you need to spend to create economic energy and rewards for yourself. So your incentive is to run as many miners as you can and spend as much dollars as you can. And then there's this race to finding a block so you can get that reward. That algorithm will always consume more energy, like always, because it has no ability to optimize itself. It's a very basic algorithm. It's been created 40 years ago by the government, I think. But the Argon 2 algorithm that we use reduces the power consumption as difficulty comes up. So it does this by mining with your memory. So memory does not take a lot of watts to operate. As difficulty comes up, the algorithm is required to carve out more memory, and your process becomes input and output bound in terms of memory usage and becomes slower. So as it becomes slower, it consumes less and less watts. So I forgot the model of that, but yeah, just looks like this. Like this is what happens. Yeah. So as difficulty moves up, GPU usage goes down, less watts, more memory is carved out, so more watts there, but the net effect of this is reducing and this is going up is memory is using 1/300th of watt of GPU approximately. So in general, so memory consumes less energy than GPU, so it's impossible to generate more wattage because difficulty increase will take the wattage down. So yeah, the utilization of the GPU percentage will be the same, but how hard it's hashing is lower. That's lower watt. And that's like very important, because so we could see this, like when we started mining with GPUs first, the GPU would spend 300 watts, and that was at the lowest difficulty the network would have. So as more miners joined, the difficulty went up, and mining wattage per GPU went down by 30%. So you went from 300 watts to 200 watts. So you're lowering your power consumption, or rather, you're distributing your power consumption among the network users, or the power consumption that you would do, they will do instead if more miners join. So it's impossible at the moment to generate more wattage, because difficulty will always take the wattage down. So and here's the thing, like, this is my opinion, because Bitcoin will always have to justify that energy usage, which will be ever increasing. So the story will always be Bitcoin is justifying it by saying, okay, number A, it's the energy usage is nothing in relating to other things like the US military complex of United States of America, or buildings that TradFi use, for example, or number two, there's a lot of excess energy that's not being utilized. You have volcanoes here and there, and so I agree with all of that. It's 100%. I'm 100% in line with that. That it's more important than a lot of other stuff, which is a subjective thought, of course, but also that there's like a lot being waste in the first place. But the number two is that, like, there's a lot of even though I agree with that, like, the woke world won't. So until they will be like forced by overwhelming like evidence after 10-20 years, which is always the case, you should listen to Lynn Alden on like the pros of Bitcoin and proof of work. She's one of the smartest people I know on Bitcoin, actually. Maybe in the sense that she's also very good at explaining stuff. But anyway, so in terms of energy usage, what we say with this is that you can theoretically reach the same level of security in the long run with a system that is not energy intense, which is a super bold statement that will outrage at least someone. So let's see what someone says. Let's get challenged on that. Let's see what I want to hear the FUD on that. So will be interesting. So yes, and the way it works is that there's this difficulty adjustment mechanism that I walked through with you last time in detail how it works. So if more miners come, the blocks per minute, it's not fixed. It varies depending on the difficulty, right? So if it increases the block production up to 72, then the difficulty goes up. So if the difficulty goes up, there's going to be less miners and less block rate happening. And if it goes the other way, then you adjust the difficulty to the other end, you reduce it. So, and that's like super cool thing, really, in itself. But the question is then, how do you make that adjustable in a peer-to-peer network? How do you find consensus of the governance of the adjustments over time? So it can work something like this, which is pretty cool, like, I think, because how it will work is that your node, your node is synchronized, and each node has its own clock. So all nodes receive the blocks in less than 1 second. And then you have block verification. So the nodes verify each block that arrives, and the node keeps record of this block, like when it arrived. And then each node calculates the mean arrival time of these nodes. And if there's a deviation, that is calculation of new difficulty adjustments. And the way it works is sort of like up here. So you could have this 10-minute sliding window where you have a set of 60 blocks, 60 blocks, 60 blocks, for instance. So what is the mean arrival time of these 60 blocks coming in? And if it increases, so that if the delta increases, then that will be a proposal for new difficulty adjustments. It's like the node is saying, guys, wait a minute, it goes a little too fast here. Like now I think we need to slow things down. We need to increase the difficulty adjustment. And the same thing if the interval, if the mean is less, that's a decrease, and they will propose a decrease of the difficulty adjustments. So all nodes do this, and when they does it, they find consensus on this difficulty adjustment. So they propose this adjustment to the rest of the network, new difficulty, and it will be the median of those proposals. And then you can finalize consensus on that for all nodes, apply to verification in new blocks, self-regulation towards blocks towards 60 blocks per minute. Okay, and then you have different protocols for how do you handle discrepancy and reach consensus finality, and how do you do with upgrades, etc. But I think it's pretty cool. It's pretty awesome, the solution. So what's cool here is that you have this power feature inherently within Argon 2, and also that you can find ways for this self-regulatory automated system to function in a completely decentralized peer-to-peer network. Yeah, so that I was pretty excited about. It's just like one of these new ideas. Like some ideas are not new, but stuff like this I haven't seen before. At least super cool. But anyway, double spend prevention. Let's talk about that. So this is important as well. How does Xenium network prevent double spending using B-tree? It's like Ethereum does with P-tree. So you can't spend anything until it's in the block that's mined. And when it's mined, it's voted by other miners as valid. And as soon as it's mined, B-tree is updated with the new balances. So this tech already is invented, it's battle tested, and it's open source, and it's easy to write. So the processes of doing this, but then you can update different additions in those processes to propagate all that data, etc. Like with B-tree. So with Zenium network, as an example, like Alice initiates transactions sent to Bob. This transaction is added to mine block, block validated by other miners. Then the B-tree is updated with the new balances, and Bob receives transactions. So here, double spending checked is also checked, and it works the same way as with Ethereum. So how Ethereum prevents double spending is different from how Bitcoin does. So let's look at both of them. Like with Ethereum, you have transactions submitted to the Ethereum network. Validators check the sender's account balance in the P-tree to ensure they have enough funds. If the enough funds is sufficient, the transaction is valid and added to a block. Now, in this step right here, they check where they check stuff. So the P-tree always keeps track of the nonce for each account. So the nonce is incremented with each transaction. So it ensures that transactions are processed in the correct order. It prevents same funds from being spent multiple times. So nonce is solves the double spend for Ethereum. So nonce is the number of transactions given from the user. Solana doesn't have this account model or nonce. They removed it. So they use proof of history instead. And but nonce solves a lot. Bitcoin. And important part to realize here too, the difference from Bitcoin is that validators are incentivized to follow the rules, and otherwise their funds get slashed. So if you try to double spend, you're sending me a transaction, and you're trying to do it with the same Ethereum dollar. You try to send both me and the crypto bro at the same time, then the validators are going to look, okay, this is the first nonce, so we're going to look at this first, and then we are going to check this balance with your account to see that you have the funds, proof of funds, and then we let it go. Oh, here come, now we check the other one, nonce number 2. Wait a minute, you're trying to send money you just sent. No, it's not going to happen. So this is what you do when you have an account model, which Zenium also has. Now, the way Bitcoin is solving double spend is a bit different, because if you're a holder, you try to double spend 1 Bitcoin. The transaction is submitted to the mempool, mempool.space, and you have a pool of unconfirmed transactions. So each node has a full history of the Bitcoin transactions, and the first transactions will be approved by the confirmation mechanism, and the second will be recognized as invalid by the confirmation process. So here's the confirmation mechanism. So checks for validation, timestamps, block confirmations, saving copies. So there's a protocol they are following to check all of this. But if it's approved by that process, the transactions is verified in the next block, and then you have a series of transactions. And if it doesn't, then it will not be accepted. But the important thing with this process is to understand, and this works indifferently from Ethereum, is that miners here instead are incentivized to follow the rules because they have an upfront cost. Okay, they have paid for that server, and it was expensive, a lot. So I want that Bitcoin. I better shape up. I better do a proper job. I'm not gonna let anyone double transact on my watch, because then daddy won't get paid. So they have an upfront cost. Now, this is an example, like understanding like how double spending works in these different systems with proof of work and proof of stake. It's interesting because what if we can then make a system where we utilize for maximum security a system where we use both parts. So the validators need to have an upfront cost, and you also need to stake and get slashed if you misbehave. So there's many different areas where this is just like an infinite amount of, there's no end to the possibilities. You remember that stream I had like a long time ago when I talked about the Lego blocks? So if you, you have 4x2 Lego blocks, you have 6 of them. For each block you add, and you can combine them in different combinations. So how many combinations can you do with 2 4x2 Lego blocks versus 3 versus 4? So if you have 2, you can combine them 24 times. If you have 6 4x2, you can combine them over, what is it, 10 million times or some ridiculous amount number, which is billion. I think 1 billion. Yeah, 950 million, something like that. So for each thing you add, like there's always like an infinite amount of combinations you can play with. So just if these are 2 factors, 2 ways how to solve the double spend, and you apply them in the system as a whole, there's many places where it's interesting to combine them. Because what we're doing when you're separating the executive layer from the validation layer, there's parts where proof of work and proof of stake is really different. And you can utilize both. But anyway, I think that's all I wanted to say with double spend. It's important to understand it. And then we talk about B-tree, which is something I don't know so much about. I'm learning a lot from this guy. Look at him. This guy, yes or no? You think he knows something about data? Like or not? Jesus. Okay. But okay, to understand B-tree, let's look at Patricia tree instead. So we covered Merkle trees last time, so you know what that is. So when it comes to storage of data, we will use probably B-tree I don't even know how to pronounce it, to be honest, but I just learned how these stuff work. So first we have to cover P tree, Patricia tree. So I'm just going to read this from the textbook. So the Patricia Radix tree, also known as the Patricia tree or prefix tree, is a data structure used for efficient storage and retrieval of key value pairs. It's similar to Merkle tree in that both are tree-based data structures, but they have some differences. The main difference between Patricia Radix tree and the Merkle tree lies in their purpose and usage. So we know what Merkle trees are. Let's understand what Radix tree, Patricia trees are, and then we go to B tree. So the Merkle tree is primarily used for data integrity and verification in distributed systems, such as blockchain networks, blockchain technology. It allows for efficient verification of the integrity of large data sets by hashing and organizing the data in a tree structure. Yes. On the other hand, the Patricia Radix tree is commonly used for efficient storage and retrieval of key value pairs, particularly in databases and file systems. It is designed to optimize search operation by storing keys in a compressed form and using a prefix-based structure. This allows for efficient lookup and retrieval of values associated with specific keys. So I think here's the kicker. In terms of structure, both trees are similar in that they're composed of nodes connected by edges. However, the specific implementation and organization of nodes differ. In a Merkle tree, each node typically represents a hash value computed from its child nodes. Like this is what we demonstrated last time, forming a hierarchical structure. In contrast, a Patricia Radix tree organizes nodes based on common prefix or keys, resulting in a more compact structure. So, like Radix tree are pretty badass in that sense because it's like an enhanced Merkle. So it's a count to value data structure used by sync node runners in the process I described earlier. So the gist of it is what you need to know is that given like a block ID and a count, you can get all the balances. Very simple. And you can get it in a 1,000th of a second. So a tree it's not part of the blockchain. It's built from it. It's part of covering mempool, the state, to a verifiable data structure. Merkle roots are used to build the blockchain, where trees are used for balance accounting. So it's a tree with a tree. Merkle roots is hashes. They're fully immutable. We don't change block contents, but we always change balances. So Patricia is mutable for balances. And think of Patricia tree as a historic record of balance changes. So it technically isn't needed, but it makes data more portable. Yeah. So sync node is both used for building blocks and updating the tree, the balances of the accounts, as I showed you earlier. I think these 3 videos, you can just screenshot them or something. Explained it very good. I like this guy. So you can see that he uses like prefixes instead of building these Merkle root hashes. So yeah, this is probably the best way to understand it. When you, I haven't found the best way to describe it yet. I haven't studied it as much either, but I know sort of how it works. I know how it works. But anyway, check that one on your spare time. Yeah, storage. But anyway, this is just super deep. But I think it's interesting to understand how all of these things work, because they are like foundation for the efficiency of creating a network. So how we are dealing with storage is super important to know, or like especially if you're going to build it. But we will use B-tree instead, which is a much more efficient. So Jack tested and got 14 gigabyte of data down to 2.8 megabyte using B-tree. So I hope he will watch this and correct me if I say anything wrong here. But that's, I think, what he told me. So it works similarly to Patricia trees, but it's easier to first understand Patricia trees. But to understand, you know what we should do, actually? Yeah, let's do that. This is what I do, guys, a lot. Like I use SendGTP a lot too when I need to learn stuff. Oops. Let's see. Yeah, okay. So what is the difference between B tree and P tree, for instance? Chat GTP version 0.2a, the latest. Look, perfect. Difference between B tree and P tree is not clear from giving information. However, based on my knowledge about three data structures, B3 and P3 are both variations of three data structures used for efficient storage and retrieval of key-value pairs. Yes. A B tree, also known as binary tree, is a type of tree where each node has two at most children. It's commonly used for implementing efficient search and retrieval operations in computer science. On the other hand, P tree, always known as Patricia tree or Radix tree, is comprised of three data structure that stores keys by their prefixes. Yes. It is designed to minimize memory usage and improve search performance by compressing common prefixes in the keys. The main difference between them lies in the structure and the way they store and retrieve keys. B3 uses binary structure with almost two children per node, while P3 uses compressed data structure that stores keys by the prefixes. Okay, yeah. Anyway, there will be a test. There will be a test on this on Friday, guys. So you need to know. Okay. Let's move on. Let's escape. So anyway, here's what here's where it becomes very valuable. So if you have the blockchain DB, the state, the raw history of all blocks and their contents, that is a packed version of all mining and transaction. So when you run and use B3, so it's indexing including all blockchain data, very fast database that takes inputs and functions like an accounting explorer. This is my explanation, how I look at it. So you have these inputs, block ID, account, and type of coin, and then you can see all the balances for this guy, this account, on this block ID had that that many. So over time, which is pretty cool. So if you're an accountant, you're gonna love this. Anyway, okay, so yeah, we're not gonna go through this. It gets too nerdy now, like debit credit operations. Yeah, let's skip that. But this is more fun. The ETH address signing stamping with hash using salt. So just like as this overview, so you can take any kind of data, you can load it into a file that goes into a block, of which miners discover Zen 11, Zen Zen 11. Sounds like heaven. Zen 11. They find heaven and become block builders. So the block is added as a hash and into the chain. Now, so when transactions to Zenium happen, and this is where we use the B tree, those are just linked into discovered block keys and hashes. So now any amount of data could be linked to this. But generally, the block is so-called stamped for the miner to assign the block to a miner, but not the hash itself. So with Bitcoin, the block is stamped, but it's not in the hash in itself. So theoretically, if you have a system like that, you could reorder blocks and take ownership. So this can never happen when you assign the stamp directly into the hash. So if you remember the live stream I had last time, we talked about the Argon 2 hashing algorithm. generator. So where we use this salt. So we specified to verify based on the key that it was a valid hash that we had found. But we used a salt, and by then we used this was it San 11, San's birthday or something like that. So everyone used that. But what's different now is we're inputting your address into the hashing salt. So what is salt? Basically, it's like this. So a salt is a piece of random data that's added before it is hashed and stored. So adding a salt to a stored password is a security process used alongside the hashing of passwords before they are stored. So think of it as an added password to make the hashing algorithm even more secure, basically. That's a much more easier way to describe it. So up until now, the salt has been 711, but now what the miner does is that it puts in your address and use that as a salt, which makes so the found. So normally, if we didn't do this, the found block is after it's been mined, coupled with the ETH address, and then it's propagated to the network for verification. But the potential risk there is that while it's being broadcasted, the block can be intercepted by cryptokines, and he will change the ETH address. You found the block, you attach your ETH address to it, you're sending it out. He takes it, removes your address, puts in his yacht address, and then sends it further. But if you do this way instead, you include it in. So when you find your block, it's really you have verifiably cryptographic hashed, proved that it's yours. So it's like self-custody built into hashing, which is pretty cool. So yeah, so that's what that is, which is also pretty cool feature. So when you're mining, you're gonna see using this address as salt. Yeah. So let's see. We want the nerd info for the hopium. Yeah. So all of this is just like just stupid fun, like blockchain stuff of just trying to hack our way into models that will be very cool. That's where it's very excited. I haven't seen Jack this excited as well. Like he's firing on all cylinders day and night, which is pretty cool. So let's just do a small recap and let me know if you have any questions. Went through a lot today. Yeah, damn, we talked about a lot. But you deserved to be talked a lot too about this. So yeah, we started with the Hidden's GPUs, and we ended up with salt. We ended up salty because we went through how to mine with GPU. It's ever changing. Soon, I think someone cracked the code how to mine. Or someone already did. It's cool because a lot of these people are in our community in this now. They weren't seniors before. They just came from other proof of work areas or wherever. You should try it out. I got so many questions on like how to mine, so I really wanted to like step by step. If you just follow these steps, you're not gonna succeed first time probably, but then you're gonna succeed. And then it's gonna feel great because it's pretty fun to do it. But yeah, let's see. People are creating a lot of stuff, so it could be very cool. main gist of everything, you're separating the delegated the execution layer from settlement layer. I mentioned it a few times. There's a separation of the two layer confirmations. All of there's been so much information, guys. It's been a lot to take in. We worked a lot. So by now, after this stream, Jack's probably updated with a few more incredible ideas as well. And the community is just making awesome, cool stuff. Would be cool if we come to a point in time, sometime, where we also can start becoming nodes. Many people can become nodes and see those data. So what's interesting here, if you check like the milliseconds, here you have a node between New York and Chicago, for instance. So you can see that it's very fast. It's just 8-9 milliseconds. So it's really like a testament that you're really down to times here. That, like, for a user, it's you can't. It's not about that either. Primarily, it's about seeing what are the first principle limitations to build up these things in the most efficient way. Elon Musk works a lot like that. Like, he breaks things down to first principles. There's a talk with Elon Musk talking about first principles from like 10 years ago or something like that, when it talks about the car industry, how he makes cars based on first principles. So the way and the way he describes it, you should really not. You should mute me now and let him talk about it, because he can talk about it much better. Like, you know, if you want to build a car, it consists of these minerals. You got to like go in the whole vertical of these mineral to see where you can make things way more efficient. For instance, it was a long time I saw it, but it was good. Yeah. So let's see. I didn't check the chat, guys. Are blocks mined pre-salt, not signed, or are also signed? So the salt is part of the input that goes into the miner. So you're taking your salt and starting mining with that data, so to speak. And when it finds, so it's the way this hashing works is that the hashing algorithm produces a key randomly, and hashing, the guessing that's done is to make all of these computations to try to find the corresponding hash to this key. So the salt goes into the production of that, the generation of that key. Accurate. Yeah, sorry, now I feel bad because I didn't check the yeah. Just stating facts with those fire-starting glasses. Nerd virgins created the internet so we can have 4K porn. How can I argue against? Simple Waters, how you doing, buddy? Yeah, anyway. Yeah, guys. This is pretty cool. This is pretty cool. I'm excited about what we can do next with this. Like how efficient, how fast can you make this network? Just look at it from the Trilangan perspective. Like, how fast can you make the transactions? How fast can you confirm it? What are the other power features by using an unlimited amount of proof of work miners as the validators of the transactions? How will that change, like a model like Solana has with leaders, for instance? That's that's pretty exciting to see. What else? Yeah, more data from the nodes, etc. But there's quite a lot of different parts about the systems. But it's pretty cool that a lot of these parts have been able to come together so fast, I think. So pretty cool. Um, um, are SemBlocks really ASIC proof? I mean, I don't dare saying anything more on like if it's possible or not. But the thing is, like, memory hard computing is what makes it ASIC ineffective, because the difficulty adjusts based on the network competition. So you're tying increased mining difficulty to memory allocation, right? So with increased mining, your machine is going to want to use more of memory than with the GPU. So an ASIC is a very specialized machine. So that interplay between the ASIC and memory makes it very super inefficient. So it makes it like very expensive, not profitable. So that's why, yes, it's impossible to mine with ASICs the way like people understand now, but who knows in the future. But by like the definition of what an ASIC is and how it works, and how the interplay between the GPU and the memory works, that seems to be the case, at least. Yeah. Cool, guys. Yeah, I think that's it. All right, let's fucking hash. See you in the chat. Ciao, ciao.